In the last couple of videos I've been talking about taking things a step further and other concepts that we'll get onto, and that's where we're at now, looking at standing waves. So a standing wave is basically a combination of those two ideas that we've looked at in the previous couple of videos, so we're looking at the idea of how a standing wave's formed, and the two scenarios that we're going to focus on is either on a string or in an air column. Not that that's the only places that we can see a standing wave, but they're the two that we'll start off with, and then we can build from there. So standing waves are formed as a result of, first of all, reflections of waves. And when we're talking reflections of waves, we're looking at them being from both fixed and free ends, depending on the scenario. And so sort of looking at an and or sort of situation depending on what type of air column and what type of with strings it's basically going to be fixed, but air columns can vary a little bit. So that's the first thing that we need to be very familiar with. The second then is superposition of waves. So once we've got a wave that has been reflected, we're then going to get the superposition of both the incident and reflected waves, and that will start to form the standing wave itself. Now, to see the standing wave, again, it's easier to look at a representation or a model of it rather than me talking and drawing diagrams. So we'll have a look at another simulation of standing waves. First of all, we're going to have a look at the incident pulse here, and we'll imagine this is on a string, but you'll notice that the ends aren't fixed at this point, and that'll become apparent as to why we're looking at it in this sense. So you can see here that that pulse is travelling to the right, so if we track a crest along, you can see there it's moving to the right. And we know that if that pulse is, or that wave is reflected from the right hand end, it's going to be inverted and it's going to travel back in the opposite direction. So if we then add the reflected pulse in blue here, you can see that the reflected pulse is travelling back in the opposite direction, and in a sense that then becomes the incident pulse for the left hand side. So we continue to get these reflections that are travelling backwards in the opposite direction that are inverted, and you'll notice here on the ends you can see that the wave is doing the opposite thing on the ends, and in the middle they're doing the same thing. Now if we apply superposition to that and we look at each point along the wave and add them together, then we get a resultant wave being the black. So you'll notice here now that the ends of the black are actually fixed in position, so it does actually behave like a string. So ultimately we don't see the blue and the red, we don't see the incident and the reflected waves, so instead we just see the oscillation of the standing wave itself moving up and down. Now if we go back and change that situation and we move to a higher harmonic, so we'll just go to the next stage up. So you can see here now the wavelength is shorter. The wave is still travelling at the same speed, but just the wavelength being a little bit shorter. If we look at the reflected pulse there, again you can see it coming back in the opposite direction, and again you can see now 2 points where the wave is moving in sync, where both the reflected and transmitted pulses are doing the same thing, and then a few points where it's doing opposite things. So if we add the resultant wave there, you can see now that we've got what looks like a sine wave that's sort of standing in place. So on the ends we've got these positions that are fixed, in the middle we've also got a position that's fixed, and then between those we've got these points where we end up with maximum amplitude. So that's the way that a standing wave is produced, just simply by the incident and reflected waves interfering and resulting in points where we get zero displacement, so at the ends and one there in the middle, and then 2 where we get maximum displacement in between. If we go up to the next harmonic above that, you'll notice again that the wavelength's a bit shorter, and we can see now that we've actually got 4 points where we have zero displacement, and we have 3 points where we get maximum displacement. If we go back just back to the second harmonic here, the other thing that's important to note here is that you can see the wave sort of oscillating between two extremes. So we can also then just add in an envelope that shows where the wave is actually travelling through. So it shows both the maximum and minimum positions of the wave, and you'll notice again in the middle there we have zero displacement, and then we get those 2 points of maximum displacement. let's go back and to the notes and add some details about how we can characterize standing waves. So we've seen that standing waves, they have a very characteristic sort of shape about them, and there are a couple of things that we can identify about standing waves. So a standing wave is basically characterized by the position of the fixed points on the wave, and we give them specific names. And so it's characterized by an alternating pattern of those points, and the alternating pattern is of, first of all, nodes. So a node is a fixed point of destructive interference. So wherever we have waves always cancelling each other out, then we'd have a node, and we're looking at that idea again of destructive interference. So when we think about superposition, that's that the two amplitudes are equal but opposite, and as a result we end up with a displacement of 0. And the other point that we have is an antinode. So if a node is a point of 0 displacement, then an antinode is going to be of maximum displacement. So in this case it's fixed points of maximum displacement. And if we're talking maximum displacement, we're really talking about the amplitude of the wave there. So fixed points of maximum displacement resulting from constructive interference. So let's have a look then at the representation we saw at the end of the animation. I'll just clip an image of it here. So here's the image that we saw at the end of the simulation, and a couple of things to note about it, as we've already talked about. So this this line here is the envelope of the standing wave. So that means that it shows the extremities through which the standing wave is going to oscillate. So you can see at the moment the position of the standing wave is sort of at the top at the beginning and then comes down at the end, and so at some later point in time these two points here are going to have swapped, so that'll have travelled down that way and that's travelled up the top, and so we'll then end up at the green dashed line to show the envelope at the top side. Now if we look at a couple of the other properties that are important to note here, notice that we've got this shape that looks like a sine wave. So the distance from one node all the way across the second node to the third gives us the wavelength. So that's the wavelength lambda of the standing wave. So it's the same definition as it is for waves in general. So the distance for the wave to repeat itself. So you can see there that the wavelength is actually equal to the string length here. We'll have a look at that relationship in a little bit more detail when we get onto sound. Just something to point out there. One last note to make there too, just about the wavelength and also the frequency. It sort of stands to reason that given that the interaction between the incident and reflected waves, they have a certain wavelength and frequency. It sort of, like I said, stands to reason that the wavelength of the and frequency of the standing wave is actually equal to that of the incident and reflected waves. So if we know what the source frequency is, then we know what the frequency of the standing wave is as well. So just finish that sentence. So that isn't basically an introduction into standing waves. There's a lot more that we can do with it when we look at the equations that sit behind it and some other applications as well. But we'll do that when we get to have a bit of a look more at sound waves, how they're generated, and some of the principles and properties behind them.